students, in the first part of the Zeeman effect, we studied normal Zeeman effect. In that, we studied that how a spectral line, when we apply external uniform magnetic field, is split up into three spectral lines. We have derived the various formulas for that splitting. Now in the second part, we will study anomalous Zeeman effect. It is when we apply a weak magnetic field, then the spectral lines split into more than three components. This splitting is called anomalous Zeeman effect. We will explain this splitting with the help of taking sodium as an example. As we all know, in sodium, we have three energy levels. This is 3s2 1/2 energy level. This is 3p2 1 by energy level 1/2, 3p2 3/2 energy level, and in this we get two spectral lines. One is from transition from 3p to 1/2 energy level to 3s to 1/2 energy level, and in this we get a 5896 angstrom wavelength. This is called D1 spectral line of sodium, and the second transition takes place from 3p to 3/2 energy level to 3s to 1/2 energy level. This is 5890 angstrom, called D2 energy line. Before explaining the lecture, firstly I wish to explain about these kind of notations. These are called spectroscopic notations. Spectroscopically, an energy level is represented using this kind of notation. Here it corresponds to principal quantum number, S corresponds to spin quantum number, L corresponds to angular momentum quantum number, for s orbital we know L is equal to 0, p orbital, p kind of notation, it is L is equal to 1, for d L is equal to 2, j is total angular momentum quantum number total momentum quantum number, which is calculated like LS coupling, like this. So now we will study that how when we apply a weak magnetic field, then how these two spectral lines, they split up into more than three components. So this will be our basic purpose of this study. For this, we will use the formulation that have been used in our previous lecture, normal Zeeman effect, that when we apply magnetic field, the energy term is introduced, that is called potential energy term, and due to which the energy of the spectral line gets changed, and that change in energy is given by this formula, where G is called Lunde-G splitting factor, whose value is given by this. We will mark this as equation number 1, as equation number 2. So now we will discuss the effect on magnetic field on D1 spectral line. So D1 spectral line involves two energy levels, and now we will discuss the effect of weak magnetic field on these energy levels. So first part, splitting of energy level. Second part, splitting of this energy level. As D1 spectral line is a transition from this energy level to this energy level, and when we apply a small magnetic field, splitting of these energy levels changes and we get some extra spectral lines. So number of energy levels into which 3 to S1 by 2 split its number of levels. It will be given by 2J plus 1, and as I just explained, for this energy level J is equal to 1 by 2, this term represents J, so it is 2 into 1 by 2 plus 1, so it is 2. So this energy level will split up into two energy levels, and Lunde-G factor for this splitting will be 1 plus J is equal to half, half plus 1 plus S. S is calculated from this value, 2S plus 1 is equal to 2, 2S is equal to 2 minus 1 is equal to 1. So S is equal to 1 by 2. So 1 by 2, 1 by 2 plus 1. Then L, I need L. L will be calculated from this. For S level, L is equal to 0. So when we calculate this, it comes out to be 3 by 4, 3 by 4, 0, 3 by 2. 1 plus 1, it is equal to 2. So for this, it will split up into two energy levels, and G factor for these two energy levels is 2. Similarly, we will calculate for this energy level. Number of energy levels into which 3p to 1 by 2 split. It is again 2j plus 1. Again j is this one. So it is 2 into 1 by 2 plus 1. It is equal to 2. So this energy level will also split up into two energy levels, and G factor will be calculated again. So 1 by 2, 1 by 2 plus 1. For S, again we use similar kind of formulation, and we will get the same value 1 by 2. For L, angular momentum quantum number, as it is P level, so for P level this value comes out to be 1. And when we solve this G value, it comes out to be 3 by 4, 3 by 4 minus 2, 3 by 2. It is 1 plus minus 1 by 2 divided by 3 by 2. 1 minus 1 by 3, it is 2 by 3. So what we get, the Lunde G factor for splitting comes out to be 2 by 3 for this energy level. Now we will calculate the energy for the splitting using this formulation. For this we need mj. For this we need mj. So now we will try to calculate the value of mj. For this level, as we know, j is equal to 1 by 2. So mj values are plus 1 by 2 minus 1 by 2. Just we now calculated the value of G for this energy level equal to 2. So we get two values of GMJ. For this combination, it is 2 into 1 by 2, 1. For this combination, 2 into minus 1 by 2, minus 1. As from equation 1, the value of delta E by this formula. So delta E has two values. For this combination, it is plus mu BB, and for this combination, minus 1 value here. So what we studied, that when we apply weak magnetic field for this very energy level, it is split up into two energy levels, one with energy this much more than the previous energy level, another with energy this one. Negative sign says this energy is less than the previous energy level, right? So now we come to this. For this again, J is equal to 1 by 2. So again mj values are plus 1 by 2, minus 1 by 2. GMJ values are again same formulation, 1, minus 1, and Lande G factor we calculated is not this one. Lande G factor we calculated 2 by 3. So GMJ values are 2 by 3 into 1 by 2, 2 by 3 into minus 1 by 2. So it is 1 by 3 minus 1 by 3. These are the two values. And delta E values from this formula, it comes out to be for this value 1 by 3 Bohr magneton magnetic field. For minus 1 by 3 value, minus 1 by 3 mu B. Again, when we apply weak magnetic field, this energy level split up into two energy levels, one having energy this one higher than the standard energy level, and this energy negative sign says less than the standard energy level. So now I will try to represent you how the splitting takes place, and later we try to find the frequencies for these kind of transitions. Say this is my 3 2s 1 by 2 energy level, and now I have explained that it has been split up into two energy levels. With mj values plus 1, minus 1, the mj value minus half, it is having energy delta E less than the traditional energy level, which is equal to minus mu BB, and it is having delta E plus mu BB. The second energy level, it is 3p to 1 by 2, and this transition it gives us 5896 angstrom D1 energy level. But after the splitting, the scenario is altogether changed. After the splitting, scenario is altogether changed, as we have just derived that the change in the energy, if I mark here dash, then corresponding to this, it will be 1 by 3 delta E. This value will be minus 1 by 3 delta E. So splitting takes place and change in energy is 1/3 of the splitting for this energy level. So we try to represent this here 1/3, that this gap here, the gap should be 1/3 than this. This is plus half, minus half. This gap is delta E minus 1 by 3 mu B. This gap is delta E. I say dash here just to change the symbol. This. So this is how the splitting has taken place, and now we try to find the various transitions from these splitted energy levels to these splitted energy levels, and we will try to see that how many transitions are possible here. We will see. So for this we will have various selection rules. So in quantum mechanics, the selection rules for allowed transitions. Delta Mj, it should be either 0 or plus minus 1, but we should take in mind that 0 transitions are not allowed. 0 transitions are not allowed. So now we will see the spectra, that what kind of transitions are there. So firstly we will see for delta Mj is equal to 0 transitions. The transitions which obey this kind of selection rule. What kind of these transitions are? So now back to the energy levels, and when we see the energy levels, the transitions with delta Mj 0, these are Mj values 1 by 2 to 1 by 2. 1 by Mj value 1 by 2 plus 1 by 2 plus. So this transition is the first transition. We will calculate the frequency for this. This Mj value is minus half. Here value is also minus half. So this transition is again delta Mj value 0. This is new 2 transition. So we will calculate these two transitions under the selection rule delta Mj 0. So I mark a line here. So first transition is from 2p 1 by 2 level with Mj half 2, 2s 1 by 2 level with Mj half. Second transition 2p 1 by 2 with mj minus half to 2s1 by 2 with mj minus half. So these two transitions are there that I have just shown you in the energy level diagram. So now we will try to find the frequency for these transitions, and the formula for the frequency that we have derived in our first lecture on Zeeman fact, that was given by this. The detailed explanation of this formula is in my first lecture. You can see that here delta nu is EB upon 4 pi m. So first level is this one, second level is this one, and we will substitute the values here and we will see what will happen. So nu is equal to, I will mark here this new one because we will have a lot many transitions, and keep on marking nu 1, nu 2, nu 3 respectively for all. For the first energy level, for this we calculate Lande G factor equal to 2 by 3. mj value is plus half. For the this state we calculate Lande G factor equal to 2 and mj value is 1 by 2. So nu 1 is nu naught plus delta nu 1 by 3 minus 1. So nu 1 is nu naught minus 2 by 3 delta nu. So this will be the frequency for the first transition taking place from this very state to this very state. Now we will try to calculate the frequency for transition from this state to this state. Again, using the same formulation, we will mark this transition as nu 2, nu naught plus delta nu. Again, Lande G factor for this energy level is 2 by 3. mj value is minus 1 by 2. For this state is 2. Lande G factor is minus 1 by 2. Nu naught plus delta nu minus 1 by 3 plus 1. It is nu naught plus 2 by 3 delta nu. So this is the second transition that we obtained under this selection rule, and these two transitions are already shown in the energy level, this nu 1, nu 2. Now for next selection rules, we will try to find another kind of transitions. So for selection rule, delta mj equal to plus 1. So we will try to find these transitions. Looking at the energy level diagram, firstly we will try to represent on the diagram those transitions which obey this selection rule. mj value plus half, this value minus half. So this kind of transition, nu 3. It is from 3 2p1 by 2 with mj plus half to 2s1 by 2 to mj minus half energy level. This will be my nu 3 transition. and for this transition I will try to find the frequency. So possible transition is from 3p to 1 by 2 with mj plus half to 3 to s 1 by 2 with mj minus half. So this transition, and now I will try to find the frequency for this very state. Same formula, nu, I mark it as nu 3, nu naught plus delta nu. For simplicity, I will rewrite the complete formula. It will make you the calculation more clear. Nu naught plus delta nu. Gi initial for this state we calculated equal to 2 by 3. Mj value is plus half. 2 for this state Lande factor minus half mj value. So this comes out to be so this is a transition from this very state to this very state. So now we come to last selection rule for Debye spectrum line. Delta mj value equal to -1, and we try to represent this transition on the energy level diagram as, so look at the energy level diagram. Here mj value is minus half, mj value is plus half. If we subtract these two, the delta mj value comes out to be -1. So this is my fourth transition, and we mark it as nu 4. And now we will try to calculate the value for this transition, as this transition is from 3p to 1 by 2 energy level with mj value minus half to 3 2s 1 by 2 energy level to with mj value plus half. So only one transition is allowed, which is from 3p to 1 by 2 energy level with mj value minus half to 3 2s 1 by 2 energy level with mj value plus half. G value for this state is 2 by 3. G value for this state is 2. We calculated just now, and we represent this transition with frequency value nu 4. Here we write the formula for the initial state, for the final state. Value comes out to be minus sign, this mj value, this is the expression for nu 4. So this completes our analysis for D1 spectral line, and if you watch the energy level diagram carefully, what you will observe that without magnetic field we have only one spectral line with wavelength 5896 angstrom called D1 spectral line from this state to this state. But when we apply weak magnetic field, we get four transitions: new 1, new 2, new 3, and new 4 transitions. We found these values, expression for these four frequencies, and this is due to the splitting of this energy state into two energy levels, this energy state into two energy levels, and this all is on the account of applying external magnetic field. And this study, when energy spectral lines is split up into large number of spectral lines, is called anomalous Zeeman effect. Dear friends, lecture is not completed because we have studied the splitting of only one spectral line, D1 spectral line. But as in the start of the lecture I explained that there exists one more spectral line, I explained as there exists one more spectral line called D2 spectral line. It is a transition from this energy state to this energy state. It is having a wavelength of 5890 angstrom value, and if you look at this carefully, we have now to study the splitting of this energy state, and we will see that into how many energy state this energy level will split and how many new transitions we will obtain. It will be studied in our next lecture, so wait for that. So please subscribe to my channel and like the anomalous Zeeman effect lecture. Thanks a lot.